In the last segment, what we have discussed, the different parameters related to fiber length, how do we express the fiber length by different methods, different parameters of expression of fiber length, and also we have discussed different parameters for expressing the fiber length distribution. Now, we will discuss here the different methods of measurement of fiber length, that is staple fiber length. First, there is a simplest method, it is a hand stapling method. This is a very simple method here. Here it is as I have mentioned in last class, here it is actually done by trained classer. So, any person, so any untrained person, if he cannot do, and if he does, it will be erroneous. So, there will be wrong result. The selection is actually it is important, we are selecting a sample and preparation of the fibers by hand doubling and drawing to give a fairly well straightened tuft of fiber about half inch. So, first we have to select the fiber, like we have selected fiber, then what we have to do? We have to double, draft and double, draft and double. In this way we have to do repeatedly to make the fiber strand fibers totally parallel. Okay. In this way we can do. Now, if we see here, if you can see here, so fibers here are drafted repeatedly. So, this is we are drafting and then it is doubling. So, drafting and doubling, drafting and doubling. In this way we are do repeatedly, so that we get a fairly straightened fiber strand, and suppose it is a black velvet, the norms is that we have to keep the fiber strand on the black velvet, and here after placing what we will get? We will get the fibers in this form. In last class also I have explained little bit. So, in this way this is the fiber strand, majority of fiber will be at the center, okay, and maximum fiber, and if the background is black here, black, then we can see through the fiber the portion which is not covered. Okay. Now, we will see a particular at the edge, there will be a clear edge we can see, and where density has suddenly changed. This is denser portion and suddenly changed. So, this is say line A and this is line B. So, right side at this point it suddenly changed. So, this we can draw rough line here, and here also you can draw rough line. So, this distance AB distance is a it is called staple length, okay. And the width is approximately width of the fringe is it is about half inch. This is laid on flat black background, okay, and thus because black background against that the white fiber normally. So, we can see clearly, and the staple length is measured. Okay. The shorter fibers will lie on the body of the tuft. It will not never go at the edge, because we have done repeated hand straightening and drafting and doubling, and we have to take precaution, we have to take care that no short fibers are lost. Okay. So, fibers, all the fibers are taken, we are not actually discarding any fiber. Okay. So, it will short fiber will lie on the body of the tuft, it will not the extreme. So, an extreme ends, that is tips, as I have mentioned, will not be the limit used for measuring the staple length. So, we will not take the extreme end into account. Okay. We will take the limit where there is a clear change in the density. Suddenly from the denser portion it has gone to the lighter portion, that we can see the clear line, rough line we can see. So, the clear the classer choose the length where there are reasonably well defined edge. So, this extreme edge is not taken, but well defined edge is there. So, between these two edges, that is the staple length. So, this is done by the experienced person, and the problem here is that it is a subjective in nature. So, different classer will land up with different evaluation for same cotton. So, this will give us a rough idea about the overall length of the cotton, but we cannot take any decision based on this result. This will give this cotton is having the longer length, this is having a short length, but it will we will not take any action on that. Okay. And so, looking at this problem of this hand stapling and judging, so there is another instrument which has been developed, which is called it is a mechanized version of this hand stapling technique. Okay. And this is known as the Surley photoelectric stapler. The principle is exactly same here, Surley photoelectric stapler, and again we can come back here. So, what we have seen here in photoelectric stapler, the same way we can prepare the fiber strand, like fiber tuft we can prepare, and here in earlier hand stapling technique we have seen the classer will decide the distance A and B, line A and B. This is based on his experience. Okay. But that subjectivity we can remove, we can eliminate by using one technique, it is a Surley photoelectric stapler, where in the same fringe is taken and the point where sudden change in density of the fibers are located. So, point A and point B will be located automatically using the photoelectric system. Now, here the system is that suppose one belt, conveyor belt is there, this is the conveyor belt where we are putting this fiber, okay, the fiber fringe. This is moving from one direction to another. So, this is suppose this fiber fringe is placed here, okay, this fiber fringe we are placing here on this end, and this is moving. Now, here somehow the light, two light source is actually projected here, two light sources, okay, L1, L2, two light sources, and the distance of these two sources are very small. So, maybe few millimeter, 1 millimeter or 2 millimeter distance at distance, and from here the sensor will give, it will after reflection it will give to one photoelectric sensor, another here, from here it is going suppose another photoelectric sensor. Okay. Now, this sensor will sense the intensity of light, this will also sense the intensity of light. Now, when the and this is moving, fiber fringe is moving along with the belt, at the center, when at the center suppose here the two lights are falling here. So, that this will give, as this is a dense portion. So, this will send the signal almost equal signal. So, this photoelectric sensor PE1 or PE2, they are receiving the light of same intensity. So, this will, and the difference of the intensity is measured, difference of intensity of this light which is received by photoelectric sensor is measured here. So, as and this is calculating the say P 1 minus P 2 this difference is measured here. So, as the difference here is exactly same, so this will give a signal of 0, there is no difference. Now, as it is moving, suppose it is moving from at this point it is giving signal, okay. It is taking signal at this point, okay. So, this is fringe is moving. So, when it is reaching at this point, at what will happen? Here the signal of one photoelectric sensor will be entirely different from another photoelectric sensor, okay. At this point, so here, so when it is reaching here, so this point there will be very high deflection, because it is a difference will be very high at this point. So, there will be a deflection. So, this point is noted. So, this is the point, suppose this is time t 1, at the time t 1 there is a maximum deviation at this point. Okay. Now, it is moving further, this is moving continuously. So, at when it is reaching at B point, the source, the light, so B point, this suppose one photoelectric sensor will give one send signal, another photoelectric sensor will send signal in entirely different way, but it will be in the opposite way. So, this way, and it has deflection, maximum deflection will be on the other side, because it is a difference. So, this time we will measure the time, say t 2. So, the time difference between these two, so t 2 minus t 1 is the time difference between these two extreme point A and B, that is and if we know the speed of the conveyor belt, then from there we can calculate the distance travelled by the conveyor belt, where there are two extreme deflections are there. So, what is this distance? This distance is the staple length. This is the thing, here it is a actually mechanized way of measuring evaluating the staple length. With this principle here, sadly photoelectric stapler works here. It is a quicker measurement of length, staple length. So, photoelectric stapler measures the staple length. It is an objective measuring technique of earlier hand stapling method. So, in earlier method what we have done, which is done by the classer does this judgment by eye, here it is a by photoelectric sensor, but technique is principle is exactly same. Okay. Here there is no subjectivity, it is an objective technique. Okay. Now, this is the principle. Okay. Now, here this is the fiber fringe I have mentioned. Okay. It is placed on some black say pad, it is placed, and this is the placed on conveyor belt, it moves gradually, and one light source is there, which is actually it gives the light, it is a light source through the lens arrangement, and it is a double slit. From here the two light sources are coming. Okay. So, this is one light source, another light source, and ultimately these are falling in two different points which are very close to each other, and from there this point the reflection, it's the photoelectric sensor say C1 photoelectric cell C1 and C2, they are receiving the light. Okay. So, when there is nothing here, so this is away from this point, this fiber fringe. So, they again that time also it is getting signal. So, this signal, the signals received by C1 and C2R will be same, exactly same. So, and this is a sensor which is actually gets signal from these two sensor. This is the meter which shows the deflection, and the deflection here is the actually difference between the signal from photoelectric cells as C1 and C2. This is the difference, and at this point as they are receiving the same quantity of light or intensity. So, this difference will be 0 here, and gradually it is moving, still it is in a black portion also it is giving the same signal, it will give, there is no deflection, but as soon as it is that particular line where the intensity suddenly changes, and that time the maximum deflection will be there. Okay. Otherwise, there will be little bit deflection, because when it is coming under this action, under the action of these fibers, there will be reflection will start, but the point where the maximum change in intensity, there will be deflection. And similarly, for other side, when it is actually releasing from this point, it is moving out, that point also there will be deflection, but deflection will be on the other side, opposite side. Now, let us see the animation here. Now, the light source is generated, this is the light source, and through it is coming through double slit, it will actually move out and going to the some mirror is there, and mirror reflects, and these are coming two sources of light and it is reflecting. Okay. Now, the fringe is coming. Now, this see there is no deflection, and at a point maximum deflection, that point has been noted down. Okay, time. Now, again it is coming, it is going to the center, towards the center. So, that center then it will be, now here as soon as it is coming to towards the center, there will be no deflection, and again it is moving out. The point with the maximum density difference will again show as the maximum deflection in other direction. So, that will give us, this is the, so this is the point, these are the points, this is the point A, and here suppose it is a point B, this distance, this is the distance, here it is a staple length. Okay. The fringe of fibers are placed, okay, over the black velvet after preparation. Why black velvet plan? Because it will give clear idea about the reflection. The density of the fringe of fibers should be such that it traces the black velvet can be seen through the central part of the where density is highest. So, the density we cannot have highly dense material. So, the density should be very thin, okay. So, that at still even through the central part, the black velvet at the bottom of the fringe should be visible. Okay. That way we have to, we cannot have very thick fringe, okay. That is important. The photoelectric stapler detects the distance between where the density gradients are maximum. Okay. The density gradients are maximum in either side. Two photoelectric cells connected opposite to each other, depending on the light intensity, the opposed cells pass a current which is proportional to the difference between the intensity. Okay. Variation in current are shown in sensitive indicator. As the fringe is advanced inside the instrument, two maximum density gradient points are detected. This distance is staple length. Okay. Maximum deflections of galvanometer in opposite direction. So, that is the distance we can calculate, and from that the photoelectric stapler, that staple length, if we multiply by 1.1, we will get a rough idea about the effective length. This is the typical equation. Next is that Combs-Shorter diagram. Okay. and this Kamm-Schroeder diagram is typically used for cotton again. Here the fibers are arranged in terms of length. Okay. Now, let us see how the Kamm-Schroeder diagrams are formed. This is the length, okay. Here is the proportion. Suppose we have the fibers, these are the fibers. So, these fibers are first we have to take, say this is O A, and here it is a, and this is the length, here is the percent of fiber. Now, the system is that we will pick by some means, we will pick the longest fiber first and we will arrange, we will put the longest fiber at the left side, leftmost side, and we will select fiber almost with a very few fibers of the same length. So, longest fiber we are putting here, the next length we will put here. Gradually length in the order of descending order by length we will put in this fashion. One care has to be taken here, which is very important, the density of alignment of placing the fiber should be exactly same. This density, like we cannot put a fiber here, it is a certain, we cannot put fiber next fiber here, there should not be gap. The gap between fibers should be exactly very even, these are the with the even. Okay. So, ultimately we will get a curve like this. This is known as the Schotter diagram. Okay. So, let us see how the Schotter diagram is formed. Now, starting with the longest fiber as I have shown. So, with the even way we are aligning the fiber. This is the Schotter diagram. Now, what is that? A Q point has been, that is OA is the length of the longest fiber. Okay, first. Now, Q is the point which is midpoint of OA, and from Q parallel to the horizontal line x axis we are drawing one line, and from that line that is intersecting a point P dash. Okay. From P dash we are drawing a vertical line, and from there we are having one point OK. OK is a point which is 1/4 of OP. Okay. And from K point we are drawing one vertical line K K dash, and we are taking half of OK. Half of OK, from half of OK we are drawing, which is point S, we are drawing one again one horizontal line which is intersecting the curve at point say R dash. So, from R dash we are drawing another line, vertical line R R dash, that R R dash is the length, and from there this is the K S is the half of that. Now, from R R dash, so O R is the length, from O R we are dividing O R into 4 equal part. Okay. So, OK O L is the 1/4 of O R. Okay. O L is 1/4 of it. So, then from L we are drawing again one vertical line. This is, that means it is a second approximation. First approximation of upper quartile length is K K dash. So, second approximation of upper quartile length is L L dash. So, effective length is defined in another way, which is the second approximation of upper quartile length is known as the effective length. Okay. And from this is n L dash. So, this is as we have mentioned earlier, the O L equal to M R. Okay. That is M R is O M is the 3/4 of O R. Okay. And from there we can calculate the dispersion percent. So, we can see O Q is the 1/4 or half of O A, then K S is the half of K K dash, O K is 1/4 of O P, that is first approximation, and O L is 1/4 of O R, that is the second approximation, and that is the length. A L L dash is the effective length, and O M is the 3/4 of O R, that is the lower quartile length. So, this upper quartile length minus lower quartile length is known as interquartile range, as we have mentioned, and from there we can calculate the dispersion percentage. Okay. And the American staple length equal to 0.91 multiplied by effective length, that we can calculate. From this shorter diagram we can also calculate the mean length. Okay. Now, the mean length calculation we must understand here how to calculate the mean length. This is just, it goes in opposite way to that of the frequency distribution curve. So, here frequency distribution is in opposite way, means here first we know the curve, then we are trying to frame the frequency distribution. In normal case we know the frequency distribution, then from that we can plot the curve. Okay. Here it is the histogram or different types of curve we draw if we know the frequency distribution, but here our curve is known. Okay. We know the curve. So, from there, and in x axis the values are fiber length in terms of say 1/8 of an inch. That means, this 4 means 4/8 of an inch, that means this is means it is a half an inch. 8 means 8/8, that is 1 inch. So, 12/8 inch like this. Okay. This is the length, and in x axis it is a cumulative frequency. Okay. So, this distribution we can calculate, we can get fiber length of 1. Now, try to see here how to get this distribution here. Now, this is the fiber length, okay, and up to say 13 or say 12, this is the 12th of an inch. Now, from there we calculate, we get the histogram here. How to get histogram? From this point, and this is the point where it is actually this point where it is intersecting, that point is at the midpoint. Now, let us see again. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, say 11. Okay. Now, say from this point we are trying to get the histogram. This is the point where now we are drawing it here, and this distance, suppose it is equal to this distance. So, and where the point it is intersecting, it is a midpoint. Okay. And this is one bar diagram. This is number 1. Now, next point is that, so this is, so length is, what is the length? Here length is 10, and width we know, width is this point, we can calculate. So, this is the, say W1 is the width. So, the area of this rectangle will be 10. Now, here it is 10, and now what we are doing? We are trying to draw another histogram here. another histogram here. Now, and from this point it is we are extending to equal point, this is second one. So, now we are trying to measure the area of this rectangle, it is almost it shows square, but it can be rectangle. Now, second one will be this one, because this is the point intersecting. So, this point, this distance equal to this distance. Okay. In this way we are forming. Now, this is another rectangle, and from this point again we are drawing another rectangle here. This is the, we are extending it up to the same point, and this is the point. So, we are getting another rectangle here. This is second one. In this way we will go. So, first if we know that this distance is, if we know this is W 1, if we know this distance W 2, this distance W 3, in this way if we know. So, what will be the area of this rectangle, or it looks about, say it is a square, this is will be the, what is the height, it is 1, okay, and this width is W 1, W 1 into 1. Similarly, what about second one? This is second one. Second one will be again the height is 1, width will be this one up to this point. So, W 2. So, this is W 2. Similarly, this one will be W 3. Okay. So, this will be 1 plus 1 multiplied by W 2 plus 1 multiplied by W 3, because we have divided into equal 1/8 of n inch in this way. So, in this way we can calculate the, this will be the total area of the curve, under the curve, that is the actually total area, and if we divide by the that width, summation of width, we will get the, if we divide the summation of width, we will get the height, mean height. So, here we can see, so this is the height, this is the height, this distance is the 1 unit, and here as per the curve we are getting 1.6 here. This distance from the 0 point, it is 4.5, this is 8.5, 13.5, 19.5, 27. In this way it is the distance. Okay. Now, here the area of this rectangle, first rectangle is 1 into 1.6. Similarly, area of this rectangle, second rectangle, this total rectangle, this one, height is 1 and width is 4.5, this is the 4.5. So, second rectangle, third rectangle, fourth, in this way we will go. So, in everywhere the height is always, it is a 1 unit. So, in this way if we calculate the mean length and total length is 64, total length it will be 64. So, this multiply divided by 64 and 7.1 is the length of the, 7.1 means 7.1 by 8 inch is the length, mean length of the fiber. So, mean length of fiber we can calculate from this Combe-Stottard diagram. Next is that single fiber length measurement. So, single fiber length measurement normally it is not done in our this industry, because it is time consuming, but for specific research or for specific defect analysis we can always do. Okay. Each fiber is taken separately and gently straightened over the slide. So, fiber you have to remove all the crimps, okay, all anything, any bent, anything, any loop type formation. So, we will have to straighten the fiber and gently put on the slide, and length is recorded. We can record the length. So, the problem is that it is tedious and time consuming process, and mill practice it is not in used, but for any research or anything we can use this process. Used where number of fibers are small. Suppose we want to measure the fiber length taking out from a yarn, small yarn. I want to know the fiber average fiber length, some I have suppose this quantity of yarn, and I want to guess this is the yarn I am it is available with me. I want to know the length of fiber. So, here from here I cannot use the Combe-Stotter principle or I cannot use any other principle, but what I can do, I can take out fiber, few fibers, and I can measure the length, okay, so that I can get a rough idea about the length of fiber. Then length measurement by weighing method. This is actually done, this is used in woolen industry and also in cotton industry. So, what it is done after combing. So, you can comb or we can do multiple drafting and drawing. Okay. The fibers are placed on velvet pad. Then what we do? We rank into groups, so that the length range in each group is about 3 millimeter. So, we are grouping the fibers of different length group, and the groups are then weighed on sensitive balance, and mean length is. So, again we can see. So, this is suppose this is the fiber length distribution. We are trying to group the fiber here. So, this is one group, we are taking the mass, second group taking the mass, third group. Mean length, this is nothing but mean length based on weight. So, from this group length group we are taking. So, W is the weight. Okay. So, from there we can calculate the mean length. So, length group is W, length group is L, and W is the mass of length group. So, W1 L1 plus W2 L2 plus W3 L3 in this way, and divided by total weight. Okay. And upper quartile length is that the 1/4 of the fibers by mass is longer than that length, that is the upper quartile length. So, the rank, first you have to rank into the groups of, so that the length are arranged, okay, arranged between the groups. Okay. So, this we have already discussed the upper quartile length. Next principle is that clamp tuft method. It is a by weighing principle. Clamp tuft method, basically this is used mainly for sliver or any parallel tuft. So, if we want to measure the fibers, length of fiber from the sliver, so what we have to do? We have to clamp the tuft first. So, this is the side view. So, here it is a clamped, the fibers are clamped with a clamp of known width. Here the width of the clamp is W, it is a known. So, after clamping, so this is clamped. So, we are removing the fibers, then we are what we are doing? We are by combing we are trying to remove the loose fibers. So, whatever loose fibers which are not gripped, these are removed. The combing, by combing it is removed. Now, these fibers are, it is a total clamped fiber. Okay. Now, after that what we do? we can cut the fiber. We cut the fiber from this which are projected from both the sides, this side and this side, we are cutting the fiber. So, combing to remove the loose ungripped fiber. Okay. Then we are, so these are the fibers which are gripped. The protruding fibers are cut, whatever protruding fibers are cut, but they are kept separately. We have to take the mass, okay, clamp and weight, we are from both the sides we are cutting. Okay. Now, then after that we are opening the clamp. In the clamp, what we will see, the fibers of this size rectangular with the parallel length are entrapped here. So, that those fiber we will weigh separately. The clamps then open and fibers inside the clamp are weighed separately. So, we have now two masses. So, one is the combed fiber masses, another is the that is projected fiber, another is the weight of the clamped fiber. Now, the total fiber mass under clamp or under combed. So, if we add these two, we will get the total fiber mass. Now, total mass of combed tuft is that mass of cut tufts. So, that is the cut tufts and mass of clamped tuft. This is a clamped tuft. Okay. These tufts were now, this is the mass of cut tuft and mass of clamped tufts. Okay. Now, these are, then this is the total mass. Now, the mean fiber length by total mass of clamped tuft, that means total mass, that is equivalent to mean fiber length if we compare with the width of the clamp by clamp tuft mass. Clamp tuft mass means this is the mass, where this is the mass of fiber of within the clamp. Here assumptions are that the fibers are arranged uniformly. Okay. They are arranged uniformly. So, mean fiber length by total mass of comb tuft, that is the total mass, it is including the clamp. Okay. So, mean fiber length we can calculate using the formula W by multiplied by total mass of clamp tuft by mass of clamp tuft. Okay. Now, if the distributions are same, distribution of the fiber is same, then mass of clamp tuft will always be same irrespective of the length of the fiber. Now, we should be very careful here, this is important. Now, suppose we have two types of fibers, this is the clamp, fiber A, fiber B. Okay. Now, these fibers are from same source, same fiber. Okay. That means same variety, same fineness. Okay. These fibers are actually arranged. Same fineness with the same fashion. Same fiber, same fineness, arranged in the same density. And width is exactly same. Okay. Now, as this width is same and here the fibers are same. Now, which one is longer? apparently the B 1 is longer, A is smaller. Now, if we take the, if we cut and if we take the only mass of this clamped mass of these two fibers, clamped mass. So, only we are trying to, we are interested in clamped mass. What will happen with the clamped mass? The clamped mass of both the fibers A and B will be equal. Okay. Clamped mass. Why? Because they are same fibers, but there this one is longer. That means, the total mass of B, total mass, total combed mass will be B is higher than mass total of A. Why? Because of its mean length. That means, total mass is actually its proportional to the mean length. Considering the same fibers, their width and everything is similar. So, this will get nullified, this will be constant approximately. So, here if we see, the mean length is approximately proportional to the mass of the combed tuft, considering that this clamped mass will be equal if the same, you are trying to say the same fiber. So, this width is constant for two fibers, the width of the clamp same width, and mass of clamp tuft is, if we assume it same. I am talking about ideally to get concept. Okay. So, mean fiber length is proportional to the combed fiber tuft, and when the mass of clamp tuft, now to generalize that it is not possible always to have the same width, same it is not always possible to have exactly same mass of the clamp tuft, it is not possible. So, we can have different. To generalize these things, we are dividing it by the mass of the clamp tuft. That is how we are getting the mass. So, this is the formula. So, width multiplied by total mass of combed tuft by mass of clamp tuft. Okay. This way we will get the mean length of fiber, it is called massed bias length. So, mean length is proportional to the mass of the combed tuft only in the case where mass of combed tuft is constant, that is the ideal case. Next is that using the photoelectric method, and which is done in fibrograph by using the fibro sampler. Okay, fibro sampler. So, as we have already discussed here, it is an optical method of measuring the density along the length of the tuft of parallel fiber. It measures the density, it is a number of fibers it measures. Samples are prepared by fibro sampler. So, fibro sampler is there. So, which actually grips the fiber from randomly from any point. So, here in fibro sampler we try to, we actually the sample, it is a length bias sample. Longer lengths are fibers with longer length are actually basically will have higher probability to get selected. So, after that, as has been explained, that final tuft is in the form of this type of form, and which are actually loop form. So, we can see once again this animation, this is the principle of fibrograph. So, this is the clamp and the scanning process is going on, light source, the scanning process is going on, and where it sorts the number of fibers depending on the density of fiber. So, its proportion of number of fibers, initially it was 100%, then it is gradually, as the distance increases, proportion of fiber reduces. So, we are getting this curve which we have seen, it is a fibrogram. Okay. And then automatically the sensor will get the data, and automatically all the parameters will be calculated. This is the way. So, fibers are clamped here, fiber 1, then it is getting loop form. Okay. In this way it forms the loop. Here we have two assumptions are there. A fiber is caught on the comb in proportional to its length as compared to the total length of all fibers in the sample. So, longer fiber has higher probability, and the point where it is caught is at random along its length. Okay. So, they can be selected at any point at random. Here is actually this is very important to understand. If we get the fibrogram, is there any relation between the Schottard diagram? What is the actually relation? Can we convert this fibrogram to the Schottard diagram? It's a totally different approach. We cannot compare the fibrogram with the Schottard diagram. So, let us see it will be very easy to understand if we take one easy example. Okay. Then we can incorporate complexity. First thing is that let us see it is a cut polyester fiber of equal length, all the fibers are of exactly same length of fiber. Now, if we try to form the Schottard diagram, let us see the Schottard diagram. This is the Schottard diagram. Now, what is Schottard diagram? We have to arrange the fiber based on the length. So, suppose this is the length, longest fiber, okay, length, and this is the proportion. This is the longest fiber, second fiber is second length, again it will be next length, third it will be again this length, so what is this? This is the diagram, Schottard diagram of polyester fiber of same length. So, this is the cut length, where we are arranging the fiber of same length, okay, Schottard diagram. Now, let us try to form the fibrogram of polyester. Now, in fibrogram, so this is the, suppose these are the fibers, polyester fibers, same length. As we have explained earlier, I have explained earlier, the assumption, first assumption that longer fiber will have higher chance to be selected is not present. First assumption is not present here. We have to concentrate on only the second assumptions. What is the second assumption? The fibers are selected randomly at any point. So, these are the fibers. Now, this is the clamp. So, one fiber which is selected. So, suppose this is the fiber, these are the fibers. Okay. Now, I am selecting this fiber. Fiber 1, 2, 3, 4, 5, 6 fibers are there. Fiber 1 is selected at the tip point. there is no end. Fiber 2 is selected, this is at T point, fiber 2 is selected here at this point. So, fiber 3 is selected at the this point, say at the midpoint. Fiber 4 is selected at this point. Fiber 5 is selected here. Fiber 6 is selected at this point, end point. Now, if we rearrange this fiber based on the length, we are rearranging the fibers. Rearranging the fibers. So, these two fibers are longest fibers. So, we are rearranging the, suppose 2 fibers, it can be 3 fibers. Next is that these fibers, these 2 fibers. So, these 2 have been selected, these 2 have been selected, next these 2. This 2 point, next is this 2. Okay. This 2 has been selected. Okay. So, next is this 2, and then say smaller some smaller fibers will be there. We can see that. Okay. Here we will see the curves will be exactly triangular curve. So, this is the probability wise any at any point fibers can be selected. So, if we try to draw the fibrogram will be typically straight line, because at this point there will be some fiber like this at this any point. So, we will see this will be the staple, and in case of cotton the things will be much more complex, because there it has got its own variability. That is why for cotton this fiber is diagram is like this, and here like this. This is the, if I draw with the black, this is for cotton, this is sorted diagram for cotton and fibrogram for cotton. It has got its own variability as well as it is randomly selected. So, fiber length variation is there, and even it has got its own variability, plus it is selected randomly and folded. That is why it is, so it will never reach that is the maximum fiber length always, it will be less than that, it is much less than that. So, now try to see here, this is the fibrogram. We can see how to superimpose the fibrogram and sorted diagram. For polyester you have seen, okay, and this is the fibrogram of cotton. X axis, the length direction is given shown in red color and proportion is shown in green color, and in shorter diagram proportion is in x axis and length is in y axis, red color, and this is the shorter diagram. Now, if we, for same fiber we are trying to superimpose just to get idea about the difference between, that is fibrogram and shorter diagram. Now try to see it is a superimposing. This is the way. This is shorter diagram, and this one is the fibrogram for same fiber. So, there is no relationship. We cannot get the same parameter from both the things. These are totally separate. We should not get confused. Okay. So, we will continue with this segment in the next class. Till then, thank you.